Today we're going to be discussing Lesson 4-6, which is about a type of problem known as a related rate problem. Related rate problems are very important. You can expect to see some on the AP test. They're also a very useful application of something that we have seen before. Related rate problems are basically implicit derivative word problems. What we're looking at in a related rate problem is the connection between the derivatives, the rates of change of two different variables. And so very similar to optimization problems, what we will be doing is looking at a relationship and taking its derivative. However, in doing problems related to optimization, we typically only had one variable and we were trying to maximize or minimize that. With related rate problems, what we're doing is looking instead at how to connect up the rate of change of one variable with another. So I have a fairly typical example for us to look at today. I think this will be the best way to demonstrate related rate problems. You already know the calculus, the mathematics that we need to use today. It's just a matter of understanding the type of problem and how we apply that math. So here we have an example. A 15-foot ladder is propped against the side of a building. The ladder begins to fall with the part of the ladder in contact with the wall falling at a rate of 2 feet per second. How fast is the bottom of the ladder moving when the top of the ladder is 4 feet off the ground? So I have an animation that we'll take a look at in just a moment, but first let's look at what this information is giving us. So first of all, we know that we have a ladder that is 15 feet long, and that of course will constrain how big these distances x and y here can be, simply because we have to have our ladder satisfy the Pythagorean theorem if the top and the bottom stay in contact with the wall at every point. So we can actually go ahead and write that out right here. We can say that x squared plus y squared must equal 15 squared, and this turns out to be the constraint. This is the equation that connects the position of the top of the ladder and the position of the bottom of the ladder here. So these two positions now are connected and related by this function. If we go ahead and look at how this function behaves when it's changing, that will give us the information we need on related rates. So let's actually go ahead and take a look at a brief animation I've put together here. You can see what's going on. What we have is we have a ladder here. Okay, so this brown segment here with endpoints A and C represents the ladder, and what we're going to do is we're going to let this ladder fall, and we're going to have it fall so that point A, the point in contact with the top of the wall, is moving at a constant rate downward, and we're going to observe what happens to point C. Now you may expect that as we do this problem, what we find is that the two pieces should move at the same rate, but it turns out that's not the case, that as one changes its motion at a certain rate, the other one doesn't necessarily keep the same rate. We'll see that here. What we have is we have two different points here that we can observe, and we will look at their changes. Point A here, the graph of point A is over here on the graph, and point C is right here. So what we will do is we will go ahead and animate this motion, and we'll trace out what the behavior looks like. Okay, and we will see here. We'll stop this in just a moment. What you see is the rates of change, the graphs of position versus time for these two points. The blue point here represents point A, the point that was up against the side of the wall. And you can see that it has a constant slope. That means its rate of change was constant, just as in our problem. But you see then that the position of the other side, the position of the point on the bottom of the wall, does not move with a constant rate. It has a rate that is changing. And the rate that this bottom portion moves with depends not only on the rate of change of the upper part of the ladder, but also depends on where the ladder is at. And we will see that here in just a moment. So what we want to do is we want to look at the rate of change. We want to see how quickly the rate of change is occurring, and this is where the implicit differentiation comes in, because what I'm going to do is I'm going to take the derivative of this expression with respect to time. Both the x and y positions that we're looking at on this ladder are changing with time, and we're going to see how that looks. So recall, when we take an implicit derivative, we basically are using the chain rule. So the derivative of x squared with respect to time will be 2x times whatever the derivative is of x with respect to time. And the same thing with y squared. The derivative of y squared will be 2y times dy dt. On the right-hand side of this equation, we just have 15 squared. The derivative of a constant is 0, and so this is our relationship. So what we can do now is we can look at this relationship, and we can relate these variables a little bit differently. We're interested in how fast the bottom portion of the ladder moves with time. This is the rate of change of the bottom portion. So this tells us how fast. Right? This is the change in position of the bottom with respect to time. That's speed. That's how fast this is moving. So let's go ahead and take this expression, 2x dx dt plus 2y dy dt, and let's solve for dx dt. Let's solve for the velocity of the bottom of the ladder. If we do that, we'll start by moving this 2y dy dt over to the right-hand side. So that gives us 2x dx dt equals minus 2y dy dt. And we can divide both sides by 2x. We see that we get the relationship that the rate of change of the bottom of the ladder is simply equal to minus y over x, the ratio of the positions of the top and bottom of the ladder, times the rate of change of the top of the ladder's position. So this is what we mean by a related rate problem. We have two rates here that are related. We have how quickly the top of the ladder is moving downward and how quickly the bottom of the ladder is moving sideways, and these are related by this particular equation. So we have now related rates, and this is a hallmark of this particular type of problem, is to find an equation or a relationship where two different derivatives are related in the equation. This is what we look for in related rate problems. So let's think about what we're given in this problem. We know that the rate of change of the top of the ladder is minus 2. Right? We were told in the beginning part of the problem that the rate of change of the top of the ladder was 2 feet per second. Those will be our units of velocity, feet per second. And it was moving downward, and that means that y, the height of the ladder above the ground, was decreasing, and that's why we have a negative derivative here. Okay, so we have minus 2 feet per second for the rate of change of dy dt. And now what we would like to do is come up with dx dt. So we can say that dx dt is going to be minus y divided by x times minus 2. Now you'll notice that the rate of change, how quickly the bottom part of the ladder is moving, actually depends on where the ladder is at. Right? The relationship here depends specifically on what x and y are. So as x and y change, that changes how fast the bottom part of the ladder is moving, even though this is a constant. Even though the top of the ladder is always moving at the same speed, the bottom of the ladder is moving at different speeds, depending on how things, what the relative positions of things are. So if you recall, in the original problem, we wanted to know when the ladder was 4 feet off the ground, what that rate of change was. So what we're told here then is we have our ladder basically looking something like this. It's a 15-foot ladder. We have 4 feet off the ground is where we are, is where the top of the ladder is at. This is our y value, and what we need now is we need our x value. And to get our x value, we simply go through and calculate the x value based on the constraint we had, the Pythagorean theorem. X squared plus y squared has to equal 15 squared. Now in this case, x squared is our unknown. Y squared will be 16, 4 squared is 16, and 15 squared is 225. So x squared will equal 209, or x will be equal to the square root of 209. We can now look at what the final rate of change dx dt is. Our equation that we came up with is negative y divided by x times minus 2. And at this particular point, we know the x and y values that correspond to things here, so we can go through and look at that. So our dx dt will equal minus 4 divided by the square root of 209 times minus 2. And this will be in feet per second. So our dx dt will be positive 8 over the square root of 209 feet per second. And that's an exact answer, so we can go ahead and leave it that way. Just a couple of comments. The first one to notice is that dx dt is positive, and a positive dx dt simply means that x is getting bigger. That is, that the bottom of the ladder on the ground is moving away from the corner. It's getting farther and farther away, whereas the top portion of the ladder was getting closer and closer. So the sign here is important. The sign tells us something about the kind of motion that we are observing. So this is an example of related rate problems. And typically what we do, the steps for a related rate problem, if we want to write those out. Okay. And again, these problems can be very different depending on the kind of situation you're looking at. We'll see some further examples shortly. But the first step is to write a relationship relating the appropriate variables. In our particular case, that was the Pythagorean theorem. And then the second step will be to use implicit differentiation to find the derivative of the expression. And then lastly, what we will do is we will plug in values that allow us to answer the problem. So we plug in known values and rates. To solve the problem. And we will be looking at related rate examples here in the future. So please look this over, watch what we've done. Again, there's not a great deal of new mathematics, but applying some old mathematics in new ways is what we're looking at today.